In this lesson, we're going to explore radicals, focusing on radical stabilities and the radical halogenation reaction. As you've likely seen, many organic reactions involve multiple mechanistic steps. Intermediates are the products of one step that then serve as the reactants in a subsequent step. You've likely seen carbocations serve as intermediates in other mechanisms. Some organic reactions involve the formation of radical intermediates. A radical is simply a species with an unpaired electron. Having an unpaired electron assures that the atom will have an incomplete octet, or an incomplete valence shell. This makes radicals very unstable, and therefore very reactive. Here I show two common radical forms, a halogen radical and a carbon radical. Keep in mind that no matter what type of structure you're drawing, whether it's a KEKULE structure, a Lewis structure, or a skeletal structure, unpaired electrons are always drawn in explicitly. The various forms of radicals can have very different stabilities. One big factor in relative radical stabilities is the size of the atom that has the unpaired electron. Larger atoms tend to be more stable as radicals than do smaller atoms. Radicals are inherently electron deficient. They may not have a positive charge, but they still have that incomplete outer valence shell. They're electron deficient. Larger atoms can simply spread out that electron deficiency over a greater space, and that makes them more stable. The halogen radicals are among the most commonly encountered radicals when studying organic chemistry. The smallest halogen radical, which is fluorine, is the least stable of the halogen radicals, followed by chlorine, and then bromine, and then the iodine radical, being the biggest of those four atoms, is the most stable. Of course, when studying organic chemistry, the most important radicals are going to be carbon radicals. There are two important structural features that greatly influence the stability of a carbon radical. The first is the degree of substitution on the carbon that possesses the unpaired electron. The more highly substituted a carbon radical is, the more stable it's going to be. You may have seen this same exact stability trend when looking at carbocation stabilities. It should make sense that both radicals and carbocations follow this same pattern of stability with respect to the degree of substitution. Both radicals and carbocations are electron deficient species. A greater number of substituents introduces a larger amount of electron density local to that electron deficient radical. Alkyl groups simply have more electrons than hydrogens. The radical can pull in that electron density, decreasing the electron deficiency and stabilizing the molecule. And just as we saw with carbocation stabilities, hyperconjugation plays a big role. Hyperconjugation is the overlap of a p orbital with a sigma bond on an adjacent atom. Well, a hydrogen atom doesn't have any additional sigma bonds associated with it. But each alkyl group attached to the radical has 3 sigma bonds which can overlap, forming hyperconjugation. Hyperconjugation is a bonding-like effect and therefore stabilizes the molecule. Another structural feature that can greatly impact the stability of a radical is resonance. Resonance can stabilize the electron deficiency of a radical by spreading it out over multiple atoms. So here we have the most important resonance-stabilized radical, the allylic radical. You might have already seen the very similar allylic carbocations and allylic anions. The term allylic simply refers to a carbon atom directly bonded to an alkene. So an allylic radical is simply a radical placed on a carbon adjacent to an alkene. You should expect the allylic radical to have resonance. Remember, resonance is all about spreading out electron density over multiple atoms. And you expect to see resonance anytime you have 3 or more atoms in a row that have p orbitals. If you look at the resonance structure on the left, you can see that all 3 carbon atoms are sp2 hybridized, and that means all 3 carbon atoms have an unhybridized p orbital. In the first drawing, we have a double bond between the left 2 carbons and an unpaired electron on the rightmost carbon. However, it's just as likely that the p orbital on that center carbon will overlap and form a pi bond with the carbon on the right as it is with the carbon on the left. And that means there's an additional resonance structure that has a double bond between the rightmost carbons and an unpaired electron on the leftmost carbon. Now you might remember, when dealing with a pi system that exhibits resonance, we can generate additional resonance structures by using the same curved arrows we use for drawing mechanisms. Now remember, we have 2 very different curved arrows that we use to show electron movement. The more common double-barbed arrows are used to show electrons moving as a pair. But now, when dealing with radicals, we need to be able to show single electrons moving. And for that, we use single-barbed or fishhook arrows, which show a single electron moving. Now, the nice thing about resonance in radicals is that it's all the same. Pretty much all resonance-stabilized radicals are going to have an unpaired electron adjacent to one or more pi bonds. And that means that the arrow pushing involved when dealing with resonance in radicals is pretty much always going to be the same. It's just a matter of having different elements and possibly different numbers of pi bonds to iterate through. So let's take a look at how we would use these curved arrows to generate the second resonance structure for our allylic radical. We start by pairing the unpaired electron with one of the electrons in the adjacent pi bond. We show this with two converging fishhook arrows, one originating from the unpaired electron and one originating from the neighboring pi bond. This will result in the formation of a new pi bond between those two rightmost carbons. Now, we still need to show where the other electron in that original pi bond ends up. It simply gets deposited on the far atom of the pi bond, and we show this again with a single fishhook arrow originating from the pi bond and placing the electron on that leftmost carbon. Another important resonance-stabilized radical is the benzylic radical. The term benzylic simply refers to a carbon atom bonded directly to a benzene ring. So a benzylic radical is simply an unpaired electron placed onto that adjacent carbon. Now, as I mentioned a moment ago, all resonance with radicals looks the same. It looks all just like the allylic radical. In fact, if you focus in on this part of the benzylic radical, you can see that it's really just an extended version of the allylic radical. And that means we can do the exact same arrow pushing to generate a second resonance structure. In this new resonance structure, you again can see here simply another allylic radical, which means we can push the electrons in the same way and generate actually 3 more resonance structures for the benzylic radical. So once you've mastered the resonance with the allylic radical, you've pretty much got it down. Each new resonance structure you generate, simply look at it and see if you've created a new allylic radical, and then do the resonance on that, draw an additional structure, and keep repeating. Again, keep in mind, all the atoms involved may not be carbons, right? Other atoms can certainly have p orbitals that can contribute to resonance. So whenever you see an unpaired electron adjacent to any two atoms that have a pi bond between them, you can treat it pretty much exactly like an allylic radical. So now that we know all about radicals and their relative stabilities, we're ready to start looking at some reactions that involve radical intermediates. The first one we're going to look at is called radical halogenation. Radical halogenation is a substitution reaction that replaces a hydrogen atom with a halogen atom. Radical halogenation is a powerful tool because it's one of the few reactions that actually can occur on an alkane. So here we show a simple example using methane. The reaction requires a dihalide, Cl2 or Br2, and heat or light to initiate the reaction. And as you can see, it simply replaces one of the hydrogen atoms with a halogen. If we balance the reaction, we can see that HCl is formed as a byproduct. Now, there's a really big problem with this reaction, and if you look carefully, you might spot it. The product also has hydrogen atoms, and that means that the product is reactive under the same conditions as the starting material. There's nothing preventing the chloromethane product from further reacting, replacing more of its hydrogens, creating dichloromethane and trichloromethane and tetrachloromethane. That's exactly what we see in this second reaction. Now you'll notice that this reaction doesn't balance. Organic chemists rarely balance reactions. It's important to realize that the product distribution really can't be easily influenced simply by manipulating the stoichiometry of the reaction. Reacting 1 mole of methane with 1 mole of Cl2 is not going to result in 1 mole of CH3Cl. And that's because reactions take time. Whether that time is 10 hours or 10 milliseconds, it's still time. At the start of the reaction, the concentration of methane is very high. And of course, the concentration of chloromethane is very low. But as the reaction progresses, the concentration of methane starts to decrease and the concentration of chloromethane increases. Now, in general, reaction rates are tied to concentrations. High concentrations make reactions go faster, and low concentrations make reactions go slower. As the concentration of chloromethane increases, the relative rate of reaction for the chloromethane starts to increase at the same time that the rate of reaction of the methane decreases because its concentration is going down as the reaction progresses. Eventually, the concentration of dichloromethane will start to increase, and therefore the rate of the reaction of dichloromethane will also increase, leading to the formation of chloroform and ultimately to carbon tetrachloride. This means that even in this simplest possible example of radical halogenation involving methane, the simplest organic molecule, you're going to wind up with four products being formed. Synthetically, this is not a good thing. If you're performing a long multi-step synthesis of some important drug molecule, you want to make one thing, right? The thing you're interested in. You don't want to make four things. But this simple reaction, even as drawn here, is important industrially. As a company, who cares what you make as long as you can sell it for profit? And it turns out that all four products of this reaction are commercially viable materials. Chloromethane is an important alkylating agent used in organic synthesis, and the other three products, yeah, those are really common organic solvents. So industrially, a company would just charge a big reactor tank with a bunch of methane and a bunch of Cl2, let the reaction go, make that mixture of products, and because those four products have different molecular weights and different polarities, they're going to have different boiling points. And that means that once the reaction is finished, you can simply separate those four components out using distillation. So let's take a look at the reaction mechanism for the radical halogenation. Most radical reactions start with an initiation step or initiation steps, which is simply the formation of radicals from non-radicals. The way this usually is done is by breaking an existing sigma bond, creating two new radicals. Now, in our example using methane and Cl2, we really only have two kinds of sigma bonds, right? We have the Cl-Cl bond and we have the CH bond. We can apply what we know about bond strengths to determine which of those two bond types is more likely to break. The CH bond, well, that's a pretty strong bond, right? It's a sigma bond between an s orbital on hydrogen and an sp3 orbital on carbon, and that's a lot of s character, and bonds that have a lot of s character are typically very strong. Hydrogen is also a very small atom, making short bonds, and short bonds are also strong bonds. By comparison, the chlorine-chlorine bond is much weaker. The two chlorine atoms are both sp3 hybridized, which means there's a lot less s character in that bond compared to the CH bond. And chlorine is a big atom. It makes very long bonds, and long bonds typically are weak bonds. So this means that the light or heat applied to the reaction is going to cause the weak chlorine-chlorine bond to break. We show the homolytic bond fragmentation using two fishhook arrows originating from the bond going in opposite directions, depositing a new unpaired electron onto each chlorine radical. It's important to realize that very little chlorine radical is formed at any point in time. This is a very endergonic step, right? Chlorine radicals are very unstable compared to the Cl2 molecule. Anytime you're breaking bonds and not making bonds, that's usually going to be very, very endergonic. So if there's a million Cl2 molecules floating around in the reaction vessel, only one or two of them are going to cleave in this way to make a handful of Cl radicals. Now, there are only two things in the reaction that a chlorine radical can bump into and react with: a molecule of Cl2 or a molecule of methane. If a chlorine radical encounters a molecule of methane, it abstracts a hydrogen atom from the molecule. Mechanistically, the unpaired electron pairs with one of the electrons in the existing CH sigma bond, creating an HCl bond. The remaining electron in the original bond is deposited onto the carbon to create a carbon radical. The carbon radical can then react with another molecule of Cl2, creating a new Cl-C bond and generating a new chlorine radical. These two steps are called propagation steps because they consume starting materials and make the actual products of the reaction, in this case, chloromethane and the byproduct HCl. The chlorine radical that's formed in the second propagation step can then go back and react with another molecule of methane in the first propagation step. This forms a chain reaction. Propagation step 1 essentially fuels propagation step 2, which then fuels propagation step 1. The two propagation steps continue, and so one or both of the starting materials, the Cl2 or the methane, are exhausted. During the course of the reaction, it is possible for two radicals to encounter one another, combining their electrons to form a new sigma bond and essentially depleting the reaction of radicals. These reactions are known as termination steps, and they can involve any two radicals pairing together. Here I show a simple example where two chlorine radicals have paired together to reform Cl2. Now, this doesn't happen very often. The concentrations of radicals in a reaction are always going to be very, very small. So the likelihood of two radicals bumping into one another is very, very, very low. This actually explains why a common mistake students make is in fact wrong. I often see students try to form that carbon-halogen bond in the second propagation step using the carbon radical combining with a halogen radical. And it's true, that will happen, and it certainly will make, in this case, chloromethane. But statistically, the odds of that happening are extremely low. The concentration of Cl2 at any point in time is going to be much, much higher than the concentration of Cl radical. The carbon radical is simply much more likely to encounter a Cl2 molecule than a carbon radical, and that makes the reaction rate of the carbon radical reacting with Cl2 much, much faster than the rate of the carbon radical reacting with a chlorine radical. So just make sure when you're drawing out that second propagation step, you're reacting the carbon radical with another molecule of the dihalide and not another halogen radical. Now that we understand the mechanism of the radical halogenation, we can use that mechanism to explain and predict several variables about the outcome of the reaction, specifically the regiochemistry and the stereochemistry of the reaction. In the example we've used so far, using methane, there was no regiochemical issue. All of the hydrogens on methane are identical. For just about any other organic molecule, regioselectivity in the radical halogenation is an issue. The radical halogenation can result in the formation of several different constitutional isomers or regioisomers. Remember that a reaction is considered regioselective when some product constitutional isomers are preferred over others. So let's take a look at the radical halogenation of a relatively simple molecule, 2-methylbutane. And we're going to start off looking specifically at radical chlorination. If you look at the structure of 2-methylbutane, you'll see that it has four unique types of hydrogen. And by unique, I mean not related by rotation or symmetry. And I've got them color-coded here. We have the blue type, we have the red type, the green type, and the black type. It's important to recognize that the black hydrogens on the right and the blue hydrogens on the left are in fact distinct from one another. There's no way we can relate the black methyl group to one of those blue methyl groups through free rotation or through a reflection. The two methyl groups on the left, however, are the same. They're related by a mirror plane that cuts the molecule in half. So overall, we have four different kinds of hydrogen on this molecule, and that means that radical halogenation, replacing just one hydrogen with a halogen, could result in four possible regioisomer products. And as you can see, the radical chlorination is not really very regioselective at all. All four products are made in roughly equal amounts. And of course, this only represents monohalogenation. It's perfectly possible that each one of these products could in fact react further with chlorine to create di- and trihalogenated products. In general, radical chlorination is not terribly synthetically useful. It might then be very surprising to see that radical bromination is extremely regioselective. Radical bromination greatly favors replacement of the hydrogen attached to the most highly substituted carbon of the molecule. Again, starting from 2-methylbutane, we see that radical halogenation with Br2 results in replacing the hydrogen attached to the tertiary carbon, above shown in red. The other possible regioisomers are formed in much, much smaller amounts. Now, the mechanism for radical halogenation is the same regardless of which halogen is being used. So why the big difference in regioselectivity when switching from Cl2 to Br2? The extreme difference in regioselectivity is due to an important concept known as the reactivity-selectivity principle. Essentially, the less stable a species is, the more reactive it'll be. And the more reactive it is, the less selective it'll be. So a less stable, more reactive radical, like a chlorine radical, is going to be less selective than a more stable, less reactive radical, like a bromine radical. A halogen radical can be transformed into a more stable species by pairing that unpaired electron with another atom to create a new bond. The chlorine radical, being unstable and therefore very reactive, isn't going to be selective about what atom it bonds with. The first hydrogen atom it encounters on a molecule is going to create a bond with that hydrogen. And that means the chlorine radical is not going to be selective. Now, the bromine radical, which is a larger atom and therefore has a more stable radical, will be less reactive and therefore more selective about what hydrogen atom it abstracts from the reactant. The bromine radical selectively targets the abstraction of a hydrogen atom on the most substituted carbon in the molecule. And that's because removing that hydrogen results in the most highly substituted radical possible, making it a very stable radical. If we go back and look at the colored version of our 2-methylbutane, removing one of the blue hydrogens would result in the formation of a primary radical. Removing the red hydrogen would result in the formation of a tertiary radical, very stable. Removing one of the green hydrogens would result in a secondary radical, and removing one of the black hydrogens would result in the formation of an unstable primary radical. Removal of the red hydrogen on the tertiary carbon will result in the most stable possible radical, the tertiary radical in this case. That means that that's going to happen more quickly than removal of any of the other hydrogens, and it's going to lead to more product. This makes radical bromination a very useful tool synthetically. The reaction is highly regioselective, replacing a hydrogen on the most substituted carbon on the molecule. And can you see how this actually solves the problem of multiple halogenations, at least in this specific example? There's technically nothing preventing the halogenated product from reacting further, replacing even more of the hydrogens on that structure. So as the reaction progresses, more and more of that 2-bromo-2-methylbutane product is going to form. Its concentration is going to go up, and the concentration of the 2-methylbutane is going to go down. But that monohalogenated product doesn't have any tertiary carbons on it. The best it could do would be to lose a hydrogen from a secondary carbon, the green carbon up above. That would result in the formation of a less stable secondary radical, and that's going to be very, very slow compared to removal of the tertiary hydrogen on the original 2-methylbutane. So while the product is reactive under these conditions, it's always going to react slower than the original 2-methylbutane. The 2-methylbutane can form a much more stable tertiary radical through hydrogen atom abstraction, and that makes reaction of the 2-methylbutane much faster than reaction of the initial formed product. And that means that multiple halogenation is extremely unlikely. So let's take a quick look at the stereoselectivity of the radical halogenation. Because radical halogenation replaces a hydrogen with a halogen, it is possible for the reaction to create a new chiral center. Oftentimes it won't. Think of the reaction with methane. Halogenation of methane simply makes chloromethane, and that's not a new chiral center. But if we look at the reaction here with butane, well, first we have a regiochemical issue to address. We do have two unique sets of hydrogen on this molecule. Since we're performing a bromination, we know that bromination is regioselective and will prefer to remove a hydrogen on the most highly substituted carbon of the molecule. Now, there are no tertiary carbons on this molecule, but we do have 4 hydrogens attached to those identical secondary carbons. And so this reaction will be regioselective, replacing one of the hydrogens on those secondary carbons to form 2-bromobutane. And 2-bromobutane is chiral. We've created a new chiral center on that carbon that now has the bond to bromine. So radical halogenation can result in the formation of several stereoisomers. In this case, it could form 2 stereoisomers, the R and the S enantiomers of 2-bromobutane. Remember that a reaction is considered stereoselective when some product stereoisomers are preferred over others. And since this reaction only makes 2 possible isomers, it would have to prefer the R over the S or the S over the R. It turns out that radical halogenation is generally not at all stereoselective. If the starting reactant is not chiral, as is the case with butane, then any new chiral center that's formed will be formed in a 1-to-1 mixture of R and S configurations. So in this case, we would actually get a racemic mixture of R and S 2-bromobutane. And of course, like all things, we can explain this using the reaction mechanism. When the bromine radical abstracts a hydrogen from butane, it forms a radical, and the carbon that has that unpaired electron is sp2 hybridized. It's trigonal planar. The unpaired electron exists in a p orbital. And remember, p orbitals have two lobes and are symmetric. When that carbon radical reacts with a molecule of Br2 to form the final product, the Br2 can approach either lobe of that p orbital. And since those lobes are identical, it's equally likely to attack one lobe or the other. Reaction with one lobe would result in the R configuration in the product. Reacting the other lobe would result in the S configuration in the product. Because the reactive site is planar and the molecule is not chiral, halogenation from each side is equally likely.